The idea mainly comes from this standardization. So if you're just doing a standardization, then, you're going to start with your data, and then you send your data. This data goes over every layer, and at the output of the layer, you're going to get a bunch of features. Finally, you get your output, right? Now, the thing is that when you go forward in your neural network, the thing that you see is that sometimes this data is actually changing in its amplitude or in its scaling, right? And this can make you trouble. One example that you already have seen, some of you, I guess, is assignment 1, right? In assignment 1, when you wanted to just recognize the pattern of X, you could work directly with 0 to 255, right? Or you could normalize everything to 0, 1, right? And then you work with it, and then finally you scale it back, right? And then those of you who did 0, 1 and 0, 255, both of them together, they have seen that the 0, 1 case is actually converging faster and behaving more robust, right? And this is the whole idea, because if you just make your data a standard within a specific bounded region to change there, then your neural network is working with the smallest scale values, all of them in the same range, and eventually everybody gets the same share when you are computing the gradients, right? So that's the key idea. The key idea is that when you have a data and this is passing through this neural network, in every part of this neural network, you see a bunch of outputs, right? A bunch of features. And these features are not necessarily scaling the same, right? So one feature might be very high, one feature might be very small, the range of them, right? And if you do not normalize them, then this could eventually end up with having trouble in training, right? Because the guy who is changing in the larger scale is going to dominate when you backpropagate. The weights are getting eventually more pronounced. The other weights are getting less observed or updated, and because of that, the model is not getting trained properly. Now, there are two different ways that you can handle this thing. One of them is input standardization. This means that the data that you have, exactly what you did in assignment 1, you just normalize the input, everybody looking the same, right? This is one way. The other thing is batch normalization, which is the one you do in between because you need it for training. Yes? Sorry? Yeah, I'm going to show it. I'm going to show it, yeah. But I simply mean like every entry, maybe they have different range of change, right? But I'm going to explain it shortly, okay? So, for instance, say you have this neural network. This neural network is a dummy one, so you have x1, x2. They are two different entries inside your data, right? So your data is x1, x2, right? Now, this data might be, x1 and x2 might be of same nature, right? For instance, they could be both value of height, right? They are both heights in centimeter, right? And they are changing in the same range, right? Maybe the height of two different people, right? Well, it's the same range, right? It's 100 something, I don't know, 140 to for say one adult, some specific region, I don't know, from 100 to 200, something like this. It's not going to be something like one of them and the other one is like 500, right? This is not happening, that extreme. So they are changing in the same scale, so they have the same mean value, they have the same variance, right? And the scale of this number is the same, right? Whereas another case is that x1 is the height, x2 is the number of children, right? One of them is changing in the order of 100 something, right? The other one is changing in the order of 1, 2, 3, 4, 5, right? Right? So they are significantly different in the value, right? And this difference in the value could impact your forward pass. Because when you are sending on, right, the guy which is 150 is going to get more impact or do more impact on the weights, right? When you are moving backward in backpropagation, you are eventually computing the weights or the gradient with respect to the weights. You get those numbers getting multiplied to your backpropagating gradients, right? And for one of them, that number is 150, for the other one is 2. So obviously, that guy gets higher gradient, right? And because of that, that weight is getting more and more updated. It doesn't mean that this is wrong. This is correct, right? Because that guy is eventually changing in higher scale. It needs different weights, right? But the issue is that this could make your computation asymmetric, right? And this could make the training like your neural network or your training is just doing a tiny bit of mistake. That tiny bit of mistake is huge for the other input, is negligible for the first one, right? So you don't want to see that. So in example A, as you, I try to show it here. If you just plot these box diagrams, then you see that x1 and x2 is roughly changing in the same interval, right? So they have same mean, same variance, same range, typical, right? Whereas for the other one of them is huge, the other one is significantly small, right? And by doing that, once you are doing the training, this is going to impact, right? So it could also make a different impact in backward pass. And the main reason is, if you think in terms of back propagation, one of them is larger, is going to impact more. The other way that you can think about it is that your empirical risk that you're computing is not having curvature, the same curvature in all directions, right? For instance, in the case A, x1 and x2, if you think about only two weights, the weights of the, for example, first layer, right? One of them is proportional to x1, one of them is proportional to x2, right? So that one that is proportional to x1, or getting multiplied with x1, is getting significantly high range, right? High coefficient. Whereas the other one is getting significantly a small coefficient, right? So this means that if you think very intuitively about the surface of the loss to be a kind of bowl, that bowl is not symmetric, right? It's stretched in one direction, is squeezed in the other direction, right? Whereas in case 1, when you have both of them changing in the same range, the scale in both directions is the same, right? And when you look at the contours, they are pretty much symmetric, right? So one of them is 150, the other one is 160, right? It's the same range, right? So here you see the curvature to be roughly the same in all directions, whereas in the other case you see the curvature being significantly different, right? And if you remember in chapter 1 when we were talking about gradient descent, we said that this guy is not the good guy, right? Because this one of them needs very high learning rate, the other one needs a small learning rate, right? And you don't like this, so what can you do? You're going to just restrict everything with this smaller learning rate, right? Which means that the higher guy is not getting trained properly. If you want to get rid of that issue, you're going to increase your learning rate. This means that the higher one, the one with higher curvature, is doing fine, but the other one is getting totally lost, right? So this is not a good idea. Instead of this one, you prefer to work with this one, because here, one learning rate is doing the job for you, right? And because of that, probably you find it better that you just do the normalization here. So what do I mean by normalization? I mean that looking at this particular difference, you try to just normalize everything first, right? So you're going to see what is the variance of what is the variance of x1. I'm going to normalize everything with that variance. What is the variance of x2? I also normalize it with that variance. Both of them now have unit variance, right? I'll work with everything. Once I am over, now if I have a new data sample, before I give it to my neural network, I just normalize it with the same variance, right? And it's going to do the job again, right? It's just the scaled version of my input. That's fine, right? And then I'm going to get what I want. That neural network is much more robust as compared to the previous one, right? So this thing could also happen in other layers. So it might be that you do the normalization here. So this is what we call it standardization. So you make every single entry standardized, meaning that everybody is roughly unit variance. And then you send them over the neural network. But once you just did the first layer, then at the output of the first layer, this y1 and y2, they show again the same behavior, right? Because in the first round of your training, one of them had like more impact, more waste, the other one has less waste, whatever, right? Who knows what is happening inside the neural network, right? So maybe these values are again changing significantly, right? And if this is again the case, like y1 is changing in a higher scale, this one is just changing in a lower scale, this is again going to do the same impact in the next layer, right? So on. And this could happen in every single layer that you have. So everybody's now clear what is the problem with normalization, right? So we need to have normalization. And there are two different forms of normalization. One of them is that you do it on your input. That is quite simple, right? You get your data. Based on the samples that you have, you compute some mean and variance. You try to make your input, every single entry, to be a standard entry, meaning that is zero mean, unit variance. So you compute the mean, the shift that is inside your data. You compute the variance of your data using the samples that you have. And then you just subtract every single sample from the mean. You divide it by the standard deviation. Then this is unit variance, zero mean, right? Roughly. You work with this data, right? Now, if you have a new sample, you just know what is the mean. You know what is the variance, right? You just simply do the same process before you pass it through the neural network. So you make the input standardized. So say, for example, you're in one particular layer. So right now, just think about the input, okay? Assume that this L is simply 1, right? And then L minus 1 is 0. This means that this Y bar that I'm talking is the standard version of the input, right? So you are going to compute the expectation of your input. You're going to compute the variance of your input. You just get every single sample that you have. You subtract it from this mean. You divide it by the standard deviation. This is going to be zero mean unit variance, right? And you pass this guy through your neural network. Everybody's clear, right? Yeah. Sorry, I didn't. We only do it in training. When you want to do inference, you need to know what is the mean and variance, which you computed before, right? Yes, yes. This is what I want to explain next. Yeah, but you average it, you estimate it using your training data set, and you use exactly the same estimate when you want to work with the new data. Then there is no problem, because then that fixed shift and the standard deviation are two fixed numbers which are not changing, right? And it's happening the same for everybody, right? Yes.
Are we doing the normalization because we want to equally weight
each input, right, right. So every input behaving the same. Everybody is zero mean unit variance, right? Yeah. But maybe one of them in the real world is just scaling is significantly a small scale, whereas the other one is just changing in a significantly larger scale, right?
But what if you have one variable that is really important? We want it to be.
That one, I mean, we do this because we want to make sure that that variable is really, the one which we detect as that variable is really the one. Because if
having a really high weight.
Right. If it has really high weight, it should not be simply because of its scale, right? Okay. It should be because of its impact, right? And neural network are going to learn it anyways, right? Okay. But you don't want the neural network to just mistake it because it has higher scale, right? Yeah, make sense? Okay. So everybody's clear? Yes? Yes, because I'm talking about random variable now, right? And then I want to just get rid of that as well. I'm going to. Yes, the bias, like this blue expectation and the variance, both of them are, I assume that I am doing it on the data distribution, right? And if I do that, then this does not depend on your sample, right? Clear? Yeah? Okay. So that one is quite fine because you have a fixed number you subtract, you have a fixed number you divide with. That's okay, right? Now the issue here is though that you don't know these expectations, right? And how we can compute that? Any idea how I can compute the expected value of, for example, input and the variance of input? I can estimate it based on the data samples that I have, right? I have 70,000 images in MNIST, for example. I just compute the average pixel value for every single pixel, right? Sum them up, all of the images, divide by 70,000. That is estimate of the average value. This is the blue guy. The standard deviation, I get that mean. I subtract every pixel from its mean, square it, again, add them up, divided by 70,000. That is variance, right? And I can, again, put it here, right? So I can estimate these values from my data set. That's OK, right? Up to this point. Now, first of all, let's see what is happening when we are doing this. When we are doing this, we would say that, OK, maybe for one part of the data set, one tiny mini batch that I get from data, right? Y1 and Y2, like I am thinking here two-dimensional, like this vector Y, this vector Y here, this is two-dimensional. It has only two entries, right? So I am just showing one of the entries on this x-axis, the other one on the y-axis, okay? I have this one. If I do not do any normalization, maybe I look at one mini batch of my data, and they are somehow distributed there, right? I'll look at another mini batch, because the mini batches are very small, right? So it's happening here, right? And it's happening with significantly higher variance, right? This one happening with a smaller variance. This one happening with moderate variance. I am exaggerating it here, obviously, because, I mean, they cannot be that significantly different if it's only two dimensions. But I want to just give you the idea, right? Because in practice, you don't have two dimensions. Those features are huge, right? And then this distinction could be really happening, right? But what you are doing, you would say that, OK, if I look at all of the data, all the mini batches that I have, and I average over them, I standardize over them, then this guy is getting here, right? I push it to the center, right, with a unit variance. This guy has high variance, but again, I'm taking it to the center. I make it unit variance, right? And so on for everybody else. So I am somehow getting any data, and then I try to put it exactly at the center. I just make it unit variance, and now I work with that one, right? The good thing is that now from one sample to another, I am not seeing some sort of, from one entry to another, I am not seeing any significant emphasis on one scaling, right? Which is going to help the neural network finding out the right pattern, right? Yes? Right.
You take that per mini batch. Is that done per mini batch, or when you check or is it done?
Yeah, this is the problem that we are going to talk about. I mean, here when you are if this guy is the input, you can do it on all of your data, right? You don't need to do it on the mini batch. That is the best choice, right? And you do it just once, right? You just compute the mean and variance once, and that's it, right? Because then you're going to just, whatever you get, you always subtract from that, divide by this, right? That's OK. You keep it forever. But the issue is that when you are training, right? Because those features in between are changing, right? Now, that is the whole issue. This is the batch normalization that we want to talk about, right? So it's not that simple for the middle features, but we need to do that. OK. So you got the idea what we're doing, right? So now, how we compute this mean and variance, obviously, we don't have the data distribution. What we can do, we can just do it based on the data set, right? So we just go over the whole data set. This is the point that we just discussed right now. You just need to go over your whole data set, right? Because your distribution could change from one mini batch to another. You don't want to change it. You want to just get one mean, one variance. You do the standardization. That's it, right? So you are going over your whole batch of data, whole samples that you have. In the MNIST case, you go over the 70,000 that you have. Doesn't matter. And I mean, 60,000 if you are doing the training. 60,000, you put 60,000 here, and then you add them up, right? That is going to be the average. You do the same thing. That is going to be your variance, right? Everybody's clear, right? You estimate this. If you have 60,000 samples, this is a fine estimate. If the estimate is wrong, it's still OK, because every sample is subtracted from the same number and divided by the same number, right? It's not going to change the fact that you're training the same thing, right? Everything is going through exactly the same transform, right? this mu that you're computing the mean value is not going to depend on the sample anymore, right? For every sample, you use the same value. This variance that you're computing is also not changing, right? Everybody's clear, right? So for the input, that's quite easy, right? For the input, you can easily do it because you have your data, right? You just compute that mean value and variance once, and that's it, right? And anytime you send a new sample, you just do the transform, right? That's not a problem. But when it comes to so the mean value is exactly the mean of your sample, data samples, the variance of your data sample is square root, that is the standard deviation, and then you can simply do this standardization. Every sample that comes in, any new sample, before you pass it over your neural network, you just subtract it from the mean you computed, you divide it by the standard deviation you computed, and that's it, right? So yeah, that's going to be this. Like for input normalization, there is no problem. You do know this u, right? Because you computed mu and the standard deviation once, right? And every time you get a new sample xp, you are first doing the same normalization, then you pass it through your forward propagation, right? But the challenge that you have is when you want to do it on the hidden layers. That is the key problem. Now, I'm a bit short in time, so I just try my best to explain what the problem is. Then, next session, we're going to just open it up a bit in terms of the backpropagation. So, now, what is the key problem here? So, say I want to do it on the first hidden layer, right? How does the first hidden layer look like? It's going to get my input, right? This input is already normalized. That's all okay. So it's going to get my input, and then it's going to pass it through one weight, and then you get your first weighted output. Then you activate it. This is your y, right? The output of your first layer. And what you want to do, you want to normalize this guy. So you need to know its mean value and its variance, right? Now, say that I just did one iteration of training, okay? If I do one iteration of training, I have one specific W, right? And now, if I want to know this mean and variance, I need to just send all of my inputs, right? I get all the features, I compute the mean, I compute the variance, I do this normalization, right? Now, I update. The weight is going to change. W1 is going to change, right? This means that y is going to change, right? And this means that the mean and variance are going to change, right? You see that? So each time I do one update, I am changing, right? So this means that after every single update, I need to send all the samples over the network, compute the mean, compute the variance, do the normalization. Is it possible? No. I mean, we ran away from this because we could not do forward-backward pass for every single sample, right? We just tried to get a mini batch because we didn't want this, right? You see what I'm doing, what is the problem here, right? But this is not the only problem. There is another problem as well. Say that Say I do the normalization, right? So this means that the normalization we had, let me see if I had it in, no, the next one is the example. So say I do the normalization. So what is the normalization if I want to normalize this guy? After I getting my y, right? Y1 is the output of the first layer, right? First hidden layer. Then I'm going to subtract it from mu1, right? And then I divide it by sigma 1, for example, right? This is going to be my normalized version, right? Now, this, if I am doing backpropagation, when I get here, say this guy is y1 bar, right? I need to compute the gradient of y1 bar with respect to the weight w1. If I want to do that, what should I do? I mean, definitely y1 itself depends on w1, right? So the gradient of y1 is going to be there. Is it the only guy? Look at that expression. Just look at this one. Is there anybody else in this equation which depends on w1? mu1 itself depends because mu1 was computed in terms of y1, and y1 coming from the first layer, right? So this guy also is there, right? Right? What about this one? It's also there, right? So if you want to write down this guy, you eventually need to write it down the gradient of y1 bar with respect to y1 times gradient of y1 with respect to w1, right? This was the only guy you had before. Now you have more. Gradient of y bar 1 with respect to mu1 times gradient of mu1 with respect to w1, right? Because mu1 also depends on w1, right? Plus gradient of y1 bar with respect to w1 times gradient of, sigma 1 times gradient of sigma 1 with respect to w1, because that guy also depends on weight 1, right? So what you see here is that your output, normalized output, is not the same thing we used when we wanted to just develop the backpropagation, right? So this means that the backpropagation is going to change, right? Even if I can handle the case where I just send all the samples every time, even if I can do it, still I am not going to move backward exactly the same as before, right? And this is a bit messy, actually, to be honest. It is one of the messy things we have in deep learning, to write down the backpropagation for this batch normalized version, right? Now, what is the idea, just in a nutshell? We cannot send all the data. It's OK. We are going to just send a batch, right? And then we use the mean and variance of the batch, but then we keep on computing the momentum over different batches, so that that momentum is somehow compensating for the change from one mini batch to another. That's the idea, that we get rid of the whole complete batch, okay? But now, once we have done it, we still cannot get rid of the second issue, which is the fact that our normalization itself depends on the mini batch. On the weights, right? And if you want to do